So we will continue with our last speaker of the session, that is Dr. Aritz Ozcariz. Aritz Ozcariz received his Master Science in Telecommunication Engineering in 2015 and his PhD in 2020 from the Public University of Navarra. His research has been focused on the study of different nano-coatings for the development of optical fiber sensors. He has performed research stays at the Universidade Tecnológica do Paraná in Curitiba, Brazil, and Università degli Studi di Desagno in Benevento, Italy, and he's currently working as a Margarita Salas postdoctoral researcher at the Department of Electrical, Electronic, and Communications Engineering at the Public University of Navarra. He's going to present now his research on periodic ratings on optical fiber tips. Please, Ari.
Thank you, Carlos, for this introduction. And yes, as you said, I'm going to discuss some preliminary work that I did last year in the University of Sannio in Benevento in Italy, in a group of Professor Andrea Cusano. And as you said, it's based on periodic ratings on optical fiber tips. My colleagues have previously talked about different kind of sensors with optical fibers. They dealt mostly with sensors based on transmission, where there were different coatings that were fabricated onto the waveguide, and the light was propagating through it. But there are many other ways to develop sensors with optical fibers, and one of them is on the optical fiber. In this case, we fabricate some structures on the tip of the optical fiber, and the light interact on this tip, on this end of the fiber, and we observe the reflection that is generated there, and we see what happens when the light interacts in these structures that are on the optical fiber tip. My main objectives when I decided to start studying these gratings on the optical fiber tip was, first of all, we tried to generate and observe lossy mode resonances on the optical fiber tip, and as you have just heard, and it's not the best way to generate a lossy mode resonance, because as Anand said, yeah, you need that the direction of propagation of light has to be as parallel as possible to the interface between your waveguide and the lossy mode resonance generating layer. So when you have this layer on the tip, you are basically perpendicular to this interface. So it's basically the worst case scenario. But the use of gratings can help with this. So that was one of the main objectives. And we also wanted to use this lossy metal oxides in combination with gratings, which actually had not been so researched before, and obviously optimizes structures to observe and create the best sensors as possible. So first of all, let me give you a brief introduction on how this structure work. Let's consider we have an infinite structure where we have a glass on one side, here on the bottom, and an outer media like air, water, or whatever, it doesn't matter, and we have a grating on the interface. And we illuminate this interface from the bottom, in this case, with a plane wave. When the wave hits this grating, the interface, a part of the light is transmitted, but due to the grating, part of the light is diffracted, and particularly there is some light that is coupled into the grating on the interface we have there in perpendicular. So that way we couple light in parallel to the interface, which is what we wanted for the lossy mode resonance. Now we have these conditions, part of the light gets coupled back, and then we can measure the reflection. In these conditions, this has already been studied. When you have this grating on a fully transparent, non-absorbent media, we have already, we kind of see a peak in the reflection, which is a GMR, guided mode resonance. This has already been studied. The peak of this resonance is located at a wavelength that is proportional to the period of the pitch of the grating and the refractive index we have outside. So it kind of it already measures the refractive index you have outside, so it's kind of work like a refractometer, so it's a sensor on its own. Now, when we try to fabricate this structure on an optical fiber tip, there are two main differences to what I just explained. First of all, it's that we have a finite area; it's not infinite, and second of all, the light that is propagating through the fiber is not a plane wave; it's an optical fiber mode, and if we see the front, it's like more like a Gaussian beam. So that will give us some differences to what we can expect theoretically from this theoretical model, to what we have on the fiber. But these two differences, it has already been experimentally studied, are not so different if we minimize them. The Gaussian beam effect is not so relevant if we consider that on the core of the fiber, the wave is quite flat, quite planar, so it's not so relevant. And the finite area issue is more relevant, but there are some ways to minimize them. One of them is to fabricate on the sides of the grating some structure called DBR, distributed Bragg reflector, which acts like a mirror, which reflects the light back from side to side. It creates somehow some kind of cavity there, which extends the effective area we have there. So minimizing this difference. So we can work with that and the approximation of the previous slide works when we translate it to an optical fiber tip. Now there are some things that we have to consider before for developing this sensor. First of all, what material we have there. We wanted to work with metal oxide because we know that this material generates lossy mode resonances, and we have to evaluate how this structure work with different material, with different optical parameters, and also the thickness of the coating we have there. Obviously, the grating period, which basically gave us the wavelength or the spectral region that we are going to work with. The duty cycle of the grating, of course, affects to the parameters of the resonance we will have at the end. The grating depth, also, it's something that will have an effect there. And we should consider that we can have some structure variations there. Well, the structure, you can see there what's basically what Arias described. We have a coating and then we fabricate the grating on the coating, or the other way around. We have a flat optical fiber, bare fiber. We fabricate the grating there, and later we fabricate the coating on top of the grating. And there are more variations. One of them is I didn't mention, but we can fabricate this structure with using a focused ion beam technology. It's basically mills grating directly on the fiber. But there are some limitations of this technology, or the one that we had in Italy, that we need to have a conductive layer on the fiber in order to be able to mill this grating there. So basically they use they fabricate a layer of gold on the fiber tip, then they mill the grating, and they remove chemically the gold layer, and this can introduce some errors, some deformities on your grating actually, or can affect your our layer somehow. So we consider that maybe we could take it as an advantage for us, and we should study what happens if we leave the gold layer on the top of the grating, and maybe it has some interesting properties that we study or not. And another possibility is the introduction of an extra layer of with different optical parameters and see how it affects to this structure. Now, in order for you to understand how I work with this, I use before fabrication, we used a software called Console that you probably already know, that allows us to simulate this structure and see how it performed beforehand, working with different parameters and how each parameter affects the overall performance of this sensor on these resonances. Now, just as an example, I have the results of some simulations on the basic structure. We have here, you can see just a period. It's not necessary to see more of the grating. In this case, with these parameters, I consider a period of 900 nanometers for the grating, a thickness of in this case, I work with tin dioxide, a thickness of 600 nanometers, a duty cycle of 65%. And this is the reflection that we got when we observe the grating with different depths, from 50 to 550 nanometers. The main effect we see is that well, with 50 nanometers depth, we basically cannot almost see the resonance. It will be here, and as we have a greater depth, the peak, the amplitude of the peak increases, and also shifts to shorter wavelengths. It's kind of logical if you see let me show you first. This is the field distribution of the electric field distribution on one period of this grating. Here with very small depths, we can see that most of the energy is concealed on the tin dioxide slab, and with greater depth, it's actually on the outside. Actually, this explains the shift on the wavelength, and in this case, the effective refractive index on this grating is lower, as we have a greater depth, that you have more, in this case, it's more water than tin dioxide. It has a lower refractive index, so the effective refractive index is lower. So the resonance is located at a shorter wavelength. In order to analyze performance, first we saw the sensitivity, and in this case, I didn't analyze the sensitivity as my colleagues in the previous slides. These structures have a different behavior, the same behavior, but have a different performance if we observe the sensitivity to a bulk change in the refractive index of the outside, or a localized change of the refractive index. And actually, when we want to later functionalize the sensors, what we actually would have in the end is a local variation, not a bulk change. So in order to analyze the sensitivity, in this case, I added an extra layer that will be a functionalizing layer once we fabricate the sensor of just 10 nanometers. And technically, when this layer senses something or some kind of analyte, it will increase in thickness a little bit. So what I measured was how the resonance shift when this functionalizing layer increased a little bit in thickness, maintaining the outer media. So in this case, the sensitivity is measured as a wavelength shift in nanometers to thickness variations, also in nanometers, for this functionalizing layer. So that's why the units are nanometers per nanometers. It's a bit different. We cannot compare it directly. In this case, the best case was when we have a depth of 450 nanometers in this particular structure. And basically I performed this study with all the possible parameters that we could have to understand how it affected the overall performance, and in order to get the best out of it. Here are what I actually got at the end once I understood how it all worked and with different structures. and this is the most basic structure. We just have we fabricate a layer of tin dioxide, and then we fabricate the grating on it. In this case, we've got a sensitivity of 0.092 nanometers per nanometers. But apart from the sensitivity, there are other parameters that should be considered for in order to better assess the performance of the sensor. It's also important to see the visibility of the resonance, which is basically the amplitude we have, and also the quality factor that's it's related to the amplitude, to the width of the amplitude. So we sum it up with a figure of merit, which is proportional to the sensitivity of the sensor, to the amplitude of the resonance, and also to the narrowness of the resonance. And we got the figure of merit in this case of 50. The second structure that I analyze and try to optimize is not the one that I mentioned before, but it's the same structure when we have a gold layer on top of it. In this case, previously we had a EMR dimension. In this case, when we have gold, what we observe in a perpendicular, in a different polarization state, it's an SPR. You already know. It's a bit different phenomenon, but it's also observable here. In this case, we have a slightly better sensitivity, but we have worse, a way worse quality factor. You can see that this resonance is way wider, and the overall performance, if we look at the figure of merit, is way worse than the previous case. Another structure that we study is, instead of gold, if we add another structure with a higher refractive index, in this case tin dioxide, we wanted to see what happened, and in this case we got a better sensitivity. That's good, but we also got a slightly better quality factor, which is a bit more narrow, and overall the figure of merit is a bit worse than in the first case. We wanted to see this because, as I mentioned, this is not a lossy-mode resonance, which was our objective, but GMR. It's not. They are somehow related, a phenomenon, I have to say, but it's not exactly the same. And we wanted to see if we could have this second phenomenon and there, but still we couldn't see that. It's only a GMR all the time. We also tried what happened if instead of tin dioxide layer, titanium dioxide layer, we added another material but with a lower refractive index than tin dioxide, in this case glass, so the same as the optical fiber. But in this case we got a lower sensitivity, so we saw that this was not, we didn't really get any added value with this one. Although we have a better quality factor, it's more narrow, but overall the performance was well. So it wasn't so interesting. Now, as I said, this was a preliminary work because well, there are still many things that we want to study. One of them was analyzing alternate grating study structures. These are very basic structures, simple gratings, but we saw that this was of great interest to see what's happening if we have, for instance, complex grating in the sense of, instead of a single grating that is periodically repeated, will happen if you have a couple of gratings with different parameters, different depths or different duty cycles that are periodically repeated in pairs as a couple of gratings instead of a single grating. We saw it's a very preliminary work, but we already saw that there are some interesting things happening there. Also 3D structure, because we have a grating that is in a single direction, but what happens if we have a periodic structure also in the perpendicular direction with a different period. We already saw that this was also very interesting and created more complex resonances of great interest. And And also, what happens if we have more freedom when when we want to fabricate? Because when I was simulating there initially, I was restricted to the conditions they had to fabricate there. They have a FIB system that they are using now to fabricate this kind of structures. But in the following weeks, we will also have this technology here, actually more modern technology, obviously, because it's new, that we have way less restrictions. For instance, we won't need the gold layer to fabricate. We can directly mill on the optical fiber, which is a great advance because, as I mentioned, the chemically removing the gold may distort our structures just fabricate. Also, we have fewer limitations in terms of depth. Now I have to restrict the simulations to a maximum depth of 100 nanometers if I want it to be realistic to what they could do there. But here we will be able to do in the future to go way deeper, at least 300 nanometers easily. We already tested that. And also in terms of the area we can actually mill. So this will give us more room to play and more possibilities to simulate more complex structures that I couldn't realistically study before. So actually, we are very excited that we are going to be able to do way more than we thought we could nowadays. As I said, this was a very preliminary work, but I'm still working on this. And that was basically what I wanted to tell you today, just a brief overview of what I have been doing. So if you have any questions, feel free to ask.
Thank you, Aritz, for your presentation. Very interesting. So we have time for one or two quick questions.
Únicamente para unir tu charla con la que ha dado Juan antes, es en las fibras de Juan, en las de CITOP, ¿se podría también hacer este tipo de patrones en la punta de la fibra?
Sí. En principio no habría mayor problema en fabricar. Habría que... Sí, porque yo entiendo que bueno, quizás habría que adaptar, bueno, quizás no, seguro que hay que adaptar. La fusión al final es un cañón de iones de galio, lanza iones sobre el sustrato en el que quieres grabar. Evidentemente la fibra óptica es un material muy duro, ya probamos cuando fuimos a hacer la demo que se lo puede grabar sin problema, a pesar de ser tan duro, y evidentemente cuando te vas a un material más blando, pues no es igual, habría que adaptarlo, porque yo entiendo, a no ser que genere mucha suciedad o se desintegre de alguna manera, que habría que analizarlo, pero bueno, en principio creo que se podría probar. Sí. Bueno, imagino que sí, pues, funciona en vacío, entonces entiendo que esto es lo que Lo que pasa es que luego sí puede ser que afecte al instrumental que hay dentro, pues todavía no lo sé, habrá que probarlo, pero en principio podría.
No sé si en inglés o en español. Bueno,
Entiendo igualmente.
en italiano, venga, vamos a tenerlo. A ver, entonces, bueno, a pesar de que no tenía los resultados más interesantes, sí que me ha resultado muy interesante la estructura con el grating en la que no quitáis el oro, ¿no?
No, realmente no es exactamente la estructura en la que no lo quitamos, sino que aquí se quitaría y se volvería a poner.
Eso, y se vuelve a poner eso, es lo que he entendido, porque si no, no tendrías lo de abajo. ¿Vale? Vale, en este caso, la profundidad del etching que hacéis es súper interesante, porque uno de los problemas, a ver, cuando tenemos capas de oro que están muy cerca unas de otras, se pueden dar lugar a resonancias muy interesantes, ¿vale?
Sí.
Entonces, efectivamente, aquí si el pitch del patrón se sintoniza bien y efectivamente se consigue un etching que consigues un comportamiento cercano, ahí se pueden dar lugar a resonancias súper chulas.
Sí.
Pero efectivamente, bueno, por lo que veo de momento, pues no es en el que mejor. En tu opinión es
Sí,
por...
bueno, esto era un SPR.
Eso es, vale.
Que no, quiero decir, llegaron efectos siempre, pero sí que es cierto que sí que vimos lo que comentas, cuando se acercan las capas de oro, ahí empezamos a ver cosas. No lo miramos mucho porque no era lo que estábamos mirando en ese momento, estábamos centrados pues, en los otros casos, sí, sin oro, pero sí que es cierto que empezamos a ver cosas ahí que eran curiosas.
Es que es muy interesante. Y luego, sobre todo, la biofuncionalización en oro es bastante
Sí.
fácil, con lo cual en esas esquinas se pueden dar sitios de una especial sensibilidad para muchas cosas. Entonces ahí sí que me parece súper interesante esto, a pesar de que ahora mismo, pues pues tú mismo has comentado que no teníais las mejores respuestas ni los mejores factores de calidad, pero vamos, me parece una línea de trabajo muy, muy interesante.
Okay. Oh, thank you, Aritz, again for your talk. And thanks to all the speakers. So we are finishing now the session, and now we have the networking session there in the corridor. So let's also thank all the people attending online to the event, and thank you very much.